Relational database design structures data into tables with defined relationships. A well-designed database ensures data accuracy, consistency, efficiency, and ease of maintenance. The primary goals are maintaining data integrity, supporting efficient queries, and allowing easy scalability. Relational databases remain crucial for enterprise systems in 2025, handling the majority of structured data workloads. Data integrity guarantees that data remains accurate, valid, and consistent over time. This is achieved through constraints and rules. Primary keys ensure unique identification of each record. They serve as a unique identifier for each row in a table. Foreign keys maintain relationships between tables. They link records in one table to records in another, enforcing referential integrity. Check constraints validate data values to fall within specified ranges. For example, ensuring marks are between 0 and 100. Row-level security provides access control at the row level, ensuring users see only data they're authorized to access. SQL standards like SQL 2023 enhance these mechanisms with JSON support for semi-structured data and advanced row-level security features. Minimal data redundancy prevents storage waste and inconsistencies. Without proper design, the same information repeats across records, wasting space and risking errors. Normalization uses techniques like 1NF, 2NF, 3NF, and BCNF to eliminate redundancy. First normal form removes repeating groups. Second normal form addresses partial dependencies. Third normal form handles transitive dependencies. And Boyce-Codd normal form provides stricter rules for complex keys. Here's an example of normalization in action. Before normalization, data repeats in full form. After, redundant information is abbreviated or separated, saving space and improving consistency. Consider this example. Instead of repeating department names in every employee record, store them once in a separate department table. Use dept ID as a foreign key to link tables. Related data is retrieved using joins. Instead of repeating information, related data is retrieved using joins. This combines data from multiple tables based on matching keys, providing complete information without redundancy. Modern relational databases offer denormalization tools for performance optimization. When needed, controlled redundancy is added to balance query speed with data consistency. Data consistency ensures that related data stays synchronized across tables in a relational database, creating a single source of truth where all information is reliable and up to date. Referential integrity is crucial for maintaining consistency. It uses foreign keys to link tables, ensuring that relationships between data are valid and preventing orphaned records. Transaction controls ensure consistency through ACID properties. Atomicity means all operations succeed or none do. Consistency preserves database rules. Isolation keeps transactions separate, and durability ensures data persists after failures. In distributed environments, consistency models like sequential consistency ensure that operations appear to execute in a logical order across multiple locations, supporting global transactions in cloud regions. The single source of truth principle requires that data is reliable, accessible to all who need it, and updated in a timely manner, eliminating conflicts and ensuring everyone works with the same accurate information. Data synchronization processes ensure that changes in one table automatically reflect in related tables. For example, updating a customer's address cascades to all their orders, maintaining consistency, and avoiding conflicting information. Flexibility and scalability ensure that a relational database design can adapt to changing business needs without requiring complete restructuring. This allows the system to grow with increasing data volumes and user numbers efficiently. Key features include modular schema design using views and indexes, which organize data into manageable components. Partitioning breaks large data sets into smaller, more efficient parts for better performance. Cloud-native features like auto-scaling enable seamless expansion of resources as demand grows. This integrates with containerized databases for efficient management in modern environments. For example, adding new columns or features should have minimal impact on existing data structures, allowing easy evolution of the database schema. Visual representations, like this database schema, show how tables relate in a modular way. The container database architecture demonstrates scalable, cloud-based organization. These principles ensure the database remains flexible and scalable, supporting long-term business growth and adaptation. Anomalies are unwanted side effects that occur in poorly designed databases. There are three main types: insertion, deletion, and update anomalies. These anomalies are eliminated through normalization, which separates concerns into different tables. This prevents data loss or inconsistencies by organizing information logically. For example, consider a problematic table that combines student and course data. If we delete the last student from a course, we lose the course information entirely. This is a deletion anomaly. Normalization solves this by separating the data into dedicated tables. A student table contains student information, a course table contains course details, and an enrollment table links them together. Now, deleting a student from enrollment only removes their enrollment record, preserving all other data. AI-assisted normalization tools can detect and fix these anomalies in real time, ensuring database integrity. Clear naming conventions, documentation, and a well-defined structure aid maintenance and collaboration. Descriptive names, ER diagrams, and metadata comments enhance understandability. Naming conventions are crucial for clarity. Use descriptive names like student instead of S to improve readability. Documentation should include code fragments, functionality statements, and references to algorithms. Write documentation before code for better maturity. ER diagrams visually represent relationships between entities, making the database structure easier to understand. Low-code tools integrate visual database design, promoting clarity for non-experts and aiding collaboration. Using meaningful names like student instead of S improves readability and maintainability, enhancing overall database design. Controlled redundancy intentionally adds some data duplication to improve query performance, but it must be carefully managed to prevent inconsistencies. This approach balances speed with data integrity. Intentional redundancy can significantly improve query performance by reducing the need for complex joins. For example, storing redundant data eliminates expensive computations during runtime. However, this redundancy must be carefully managed to avoid inconsistencies. Without proper controls, duplicate data can become outdated or conflicting, leading to data quality issues. One common approach is using denormalized views or materialized views. These store pre-computed results from multiple tables, allowing faster queries without repeated joins. Triggers are used for synchronization, automatically updating redundant data when the original data changes. This ensures consistency across the database. In-memory databases optimize controlled redundancy for analytics workloads. By keeping data in memory, they provide lightning-fast access to redundant but carefully managed data structures. For example, storing calculated values like total marks in a result table can dramatically speed up queries. Consistency is maintained through triggers that update this redundant data whenever underlying scores change. In summary, controlled redundancy strikes a balance between performance gains and data consistency, using tools like views, triggers, and in-memory systems to manage intentional duplication effectively.